Today we will talk about modern convolutional neural networks, particularly one of the basics one, residual neural networks. You can see its structure to the right. Today we will talk about BatchNorm, ResNet, and training loop, how you should organize training of your models. So at the core of batch normalization lies the idea to somehow rescale and center within each batch of data. You know, we train models most often in a batch gradient descent. That's why the scope for this is a batch. So the idea of faster and more stable training through normalization of the layer inputs by recentering and rescaling is called batch normalization, and I advise you to use this layer within your custom models. Here you see the parts of the batch normalization. The two of them is a batch mean and the batch standard deviation. This B denotes that this is a batch. It is at 32 samples or 16 samples or 8, whatever how much you take for a one batch, and see it's a normalization per number of samples in the batch. And the mean is just, you summarize all the samples and you divide by the number of the samples. Standard deviation is average deviations, and then you add this epsilon here just because it's in the denominator in the other formula, and you need this very small number to make it not zero. And then for every sample, normalize it, you rescale it by applying BatchNorm. You take every sample in this batch and you subtract calculated mean batch-wise, and you divide by variance. Pay attention to these two parameters, gamma and beta. Those are learned parameters in the batch normalization. So this is a fitted layer, and those are two additional parameters to fit. In general, it looks like this. Activation function and input activation function now is not only a multiplication of weights and input plus bias, but this data is passed to a batch normalization layer. Here is implementation of BatchNorm. You have x hat, it's average x minus x moving mean divided by moving variance plus epsilon, the square root of this. Moving mean calculation, this one, and the moving variance calculation, this row. As a result, you have output of a BatchNorm, this gamma, learned parameter, multiplied per x hat calculated here, and plus b beta. Now, if we turn it to a layer because of the learned parameters, then we have to say that gamma and beta are fitted parameters by torch so that we calculate gradients for them. And then we fulfill these parameters that will be recalculated for each batch, moving mean and variance. And here is a layer behavior, this major function like forward propagation, moving mean calculation, BatchNorm that you saw on this screen. Then the rest of the parameters are just set like momentum and epsilon. Now, what is a ResNet? The regular computer vision layer looks like this. You have an input, you have weights, you have activation function, and you have another weights layer. So usually you multiply input per weights, you add bias, you put all of that into activation function, and then you get some activation. You use this activation as input to the next layer. Literally, you again multiply it by weights, you add bias, and you put it into the next activation function. Here, the problem arises with time when you backpropagate from the last layers to the first layers, your gradients decay so much, so the information do not propagate anymore. To fix this situation and have actually deeper networks, this approach of adding a residual block was invented, input, and you add it to activation of the next layer, skipping a whole layer. They also call it skip connections because you skip some amount of layers. The forward propagation happens here, but then you add to this activation values raw inputs of X. This approach allows to get a deeper neural network without losing gradients. Here you can see to the right, how is it implemented? A residual block. You have convolutions, skip connection here. The whole idea of a convolution is to add Y plus X. X, as you see, is a convolution 1 by 1. So it's not raw X, but it is somehow permuted within itself. but then you add this almost raw X value to the transformed activations that you got from your two layers here. You convolved once, you put it to a BatchNorm layer, you got Y. You convolved Y second time through BatchNorm layer, and then you added this result of a skip connection, the raw X permuted with a 1-by-1 convolution. You added it to this output of all of the previous actions, and you return it as a arrow activation here. See, so you just add up to a typical way how you do convolutional neural networks with this skip data that surpasses the majority of the layers. And it allows to build way deeper neural networks. Currently, ResNet is a modern benchmark and typical first network that you try for computer vision to classify something or detect something. And you can see how it is built. It has a lot of the skip connection blocks. Here, how it is implemented. So we have something that is called the residual block. Then we have convolutions. We have batch norms, max pooling. This is a typical block. Then you have a layer, a function, make a layer makes a residual block, and then a classical block. See, and then you just repeat it, and then you just changing inputs. As a summary, you can see that its structure, it can have dozens and hundreds of layers. This skip connection allows us to preserve gradients and actually train it. Now let's review the training loop. It is very typical, and you will repeat it in all the applications. Anything that you will implement now and then, it's all the same. Usually you load the data. It's in build data set fashion NIST. It exists within a standards data sets of PyTorch. This is just to pass to the data. You can download, see, train and test separately. So you call it training data and test data, and this is just a label. Is it a train or is it a test? And now you can say whether to download it every time, or if it's downloaded, then just skip it. And then you can already transform it to a tensor. So it is the first augmentation, and it's done for you here before you download the data. After downloading the data, you create data loaders. Data loaders are iterators that will feed data into your model. Think of it as a yield function. Each time you call data loader, it returns you a batch of data. And that's why to initialize the data loader, you give it a path where your data, which data set it will provide to you, and batch size, how many sample it returns you every time you call it, and from which source. Then you do the training for X and Y in test data loader, do one iteration, print what is X and what is Y. Then define and initiate the model. As you might guess, initiation happens here, the same as in object-oriented programming. Initiation is when you create an instance of the class. So first you define the class, and then you create an instance of this class. You send this object, the instance of this object, to some device. Your device could be CPU, GPU, TPU, or other computational resources. Let's revise what we have in implementation of the model. Here you have two major functions. You have a constructor and you have a forward. Forward is the same as inference. Yeah, it's a forward propagation from the beginning to the end of your network. Yeah, and it returns what? It returns what you defined here. So the architecture, here you define the architecture of your network. You call a constructor of a superclass, and here you define layers. They are not created here. This is a definition. The same as in the constructor of a class. You define what fields and what methods you will have. Here you define what elements of your network you will have here. And remember, this sequential block is just a list of layers in the order of a forward propagation. And then you define forward function. In the forward function, you define and you decide how your layers declared here work with your inputs. So X is the input and you can call it whatever, it doesn't matter. The point is that here you created instance of a flattened, see? And now here you say that you take this X inputs and you put it to your layer, your object that you declared here. So first you pass it to the first layer you declared here, and then outputs of this layer, you pass to a second object that you declared here. of this structure. And then you return logits. The logits are outputs of this layer. In this case, these are the logits: input channel size and output channel size. So this layer will output vector of size 10. Each value of this vector will be some value. We call them logits. So that's the raw output, and you still have to put it to error function. There is no error function here. So this is your network. When you call neural network, it will implicitly call the forward function. So if you call model and you pass it some data, it will call forward function. Now, the fourth thing that you define is that you define a loss function and optimizer. Loss function have to correspond to your goal. In this case, this is a cross entropy loss, and it's defined to predict classes. See, you have 10 output logits. That's why cross entropy loss was the choice. It will help you to turn it into probabilities and map to unknown class labels. And then you select optimizer. Again, optimizer is your choice. Here, the simplest one has been taken. It's stochastic gradient descent. Important that you have to pass to an optimizer function parameters to optimize. If you define any parameters outside of the model to optimize, you also have to put them here. Otherwise, they will not be optimized. And the other hyperparameter that was set here is learning rate. Again, that's a decision. You can use different hyperparameter tunings method to find the optimal hyperparameters. The fifth thing that you do is you define training and testing loops. Here is a training loop and here is a testing loop. Those are functions. They are very typical. If you figure out how to write them once, you will not have problems anymore for any kind of model because they are 90% the same. The idea is exactly the same. So the train function takes as input a data loader. Remember data loaders? You might guess that the train will get train data loader and test will get test data loader. Then it gets model, a model that you instantiated here, an instance of your neural network class. Then it gets as an input a loss function. Again, loss function of your choice and corresponding to your task. And then it uses as an input an optimizer. The algorithm that you decided to use to optimize weights of your model, which you pass here, with the learning rate of your choice. Then you're ready to train. What happens inside the train function? First, you need to know how many samples do you have to iterate over. So you ask, what is the length of my data set? And then turn the model into the train mode. Train mode means you can edit the weights and you calculate gradients. As an opposite, in the testing function, you turn the model into evaluation mode. Evaluation mode means that the gradients are not calculated and only forward propagation is performed. Here, forward and backward, gradients are calculated, weights are changed. Here, weights are fixed, only forward propagation is performed. Training loop. So here you get your data loader and enumerate it. Enumeration gives you index. It returns you a value of a generator, which is pairs, tuples of X and appropriate Y, and date, inputs, and label, and index. Your index is batch. Batch is just the number of the batch. It's like 1, 2, 3, 4, 5, 6, and these are the pairs of the batches. So if you chose your batch size to be 32, it will be a 32 samples of inputs and 32 labels. Then you put them to appropriate device. If you decided to train on GPU, this is important because you have to send those weight to appropriate computational device. If you do not send them to GPU, even if you have GPU, it will not be used. Then you compute prediction error. Take instance of your neural network and you pass X, your inputs. What it does, it calls forward function. Forward function does forwarding all the inputs through your layers and it returns you logits. We call logits prediction because those are predicted value. Then we take predicted values and we put predicted values along with the ground truth labels to a loss function. You might guess what loss function does. It calculates loss. So here your function calculates loss and you know how far are you from the ground truth labels. Then, knowing the loss, we can calculate gradients for each layer and perform backpropagation. So here we just remove potentially any gradients that we got from previous iteration, and we perform backpropagation. Backpropagation, we calculate gradients for each layer. Once we calculated gradients for one layer, we can go deeper backward and deeper until we reach the initial input layer. Then we perform a step of the optimizer where it optimizes weights. It uses gradients to change the values of the weights. This is just a logging of the results. See, every 100 batch calculate loss, and we just report. The loss is like this. Testing is similar to training, but we do not calculate gradients and we do not update weights. We do not perform backpropagation, turning the model into the evaluation mode where we do not calculate gradients, set up initial values of a test loss and the correctly predicted values by 0 just to nullify it. And then with torch no grad, pay attention. With say PyTorch, do not calculate gradients. We do iteration for every tuple of inputs and labels in our data loader. I'll remind you that this is not singular samples. Those are a batch of 32, for example, values of inputs and 32 labels. Again, we send them to the device. The model performs prediction. We calculate rolling test loss. See, we calculate loss function. Loss function, again, gives us loss here. It gives us loss between predicted and ground truth and summarize it. It's called running sum of test losses. Then we calculate number of predicted values. Yeah, literally in our predictions, we take the index of the largest value and we check is this index is the same as the index of a ground truth label, and then we just sum them up. Then we divide the total test loss and the total correct sample. We divide by the number of batches to know the average test loss, and we divide by the size of the data set to know the accuracy. And at the end of testing, we print our test accuracy is like this, our average loss is like this. Here is an example, training and testing. You see, after we defined its training functions, then we decide how many epochs runs through from the beginning to the end of all the data set do we want to have, and we perform this training. Please notice that at the beginning of training, our loss is larger and accuracy is lower. And in 5 epochs, it increases, but yes, still it desires to be better. Why? Because we could perform more epochs and have better accuracy. Or we might have different network architecture.